Welcome everybody. Welcome to this first Movella Sports Conference. The Sports Conference is about combining sports and kinematics. And today our aim is to give you valuable insight into different tools that can be used and combined for performing analysis in research and in sporting environments. This also includes a detailed look at the latest innovations for measuring human motion in sports, such as EMG, force plates, but also software applications that can calculate kinematics. During this sports conference, our speakers will share their insights about the technology and the application in motion capture. We hope that by showing the innovative combination of analysis tools for researchers and sports scientists, that they will learn new ways to investigate an athlete's performance capabilities. Hello, everybody. Welcome again this afternoon at the next presentation on our sports conference. It's 2 o'clock, which means that it's time for Heiko Wagner of the company called Predimo, which stands for Prediction of Movement, is going to present.
Yeah, thank you very much to you, Xsens team, to giving me the opportunity or giving us the opportunity to present here our possibility or the way how we are predicting joint forces and ground traction forces based on our computer model. And thank you very much for the audience to take the time to listen to that talk. First of all, I would like to show you a small video. And if you look on that video, the question arises, why do these guys do that? That's the first question from my mind. I think it's fun to do. But the second question is, how can we measure the movement of these guys in this really strange environment? And how can we measure, for example, the external forces here on the ground? And even more important, how can we measure maybe internal forces? So to answer the question, is maybe the stress or the loading in the joint too high for these experts here, and or how could they change maybe their movement in order to reduce joint loading and so on? This is the basic idea what I would like to talk about in the next few minutes. So this is the agenda of my talk. It's a short introduction about what we are doing with the computer modeling. Then 2 examples. The one is the prediction of joint forces, and the second is the prediction of ground traction forces. As easy as that. Okay. So first, if I ask you in the introduction, which load or which forces are acting, for example, in the knee joint or in the ankle joint of this sportsman, or while you are running outside in the wood or something, then we have to admit that it is not possible to measure that in vivo, because then we have to place a force transducer into the human body, and this is from ethical reasons and because of the pain you will feel, not a good idea to do that. So it is still a problem to get that information. But the nice thing is that there are certain situations where it was possible to measure the joint forces while in a living human, while they are performing walking or squatting or other movements. And this was done, for example, here in that very nice study, which was done by Taylor and from the Institute of Biomechanics by the ETH Zurich and the Charité in Berlin. And I'm very thankful that they gave me the data for that, and we were able to use that as a validation tool to check our computer program as well. And what they did is, you will see that here in the video, the subject is doing a squatting movement, for example, here, and you can see this is the prosthesis. So this patient got this prosthesis, and here on the top of the tibia, in the tibia plateau here, they have introduced a force transducer, and they were able to measure the knee forces, or better said, the forces on that tibia plateau in all 3 directions. Yeah, And they measured also with a Wagner system here, the kinematics and some ground traction forces. And as you can see, they have got this data during squatting for the ground traction force and the in vivo forces in the knee joint. And now I go to the next slide, and these are this is the picture that I showed you already. And what you can see, as expected, the ground traction forces are around 400 newtons under each foot. So red and blue means the left and right foot. And so in the mean, we have roughly 400 Newton, means that the subject would be 80 kilograms. So below 1 foot, we have 400 Newtons. And in this knee joint, you measure about more than 2,400 Newtons. And here we can ask the question, where do these very high forces are coming from? So on the one hand side, we have an external force of only 400 Newtons, but in the knee joint, we can measure 2,500 Newtons. Where are these 2,000 Newtons coming from? And for most of you or some of you, you have already an idea where it's coming from. It's like in this sportsman I showed you in the first video, you have this external force. So for the squatting movement, this was, let's say, 400 Newtons. And therefore you have the 400 Newtons, and these 400 Newtons are also here roughly in the knee joint. But additionally, the 400 Newtons do acting because of a lever arm. They are generating here a torque in the knee joint. And this torque in the knee joint can only exist if there is a counter torque in the knee. So, and the counter torque must be generated, in this case, by muscle forces. So we have a shorter lever arm here for the muscle. Let's say this is a respective muscle here, and you see that if this torque, which is then generated by the external force, must also be generated by the internal forces. And so the same torque here in green and the external force must be generated by the muscle force. And if we have these two equations, we can rearrange them and see, we can calculate the forces depending on the lever arms that we have and the external force. And if we assume, let's say, these 400 Newtons, and let's say the external lever arm is 20 centimeters and the internal is, let's say, 4 centimeters. I have chosen these numbers to get simple calculations. Then you will get roughly 2,000 Newtons of muscle force, which is necessary to generate this internal torque. And if you add both, then you are roughly in the area of 2,400 Newtons. And this is what we have what they have measured with their instrumented implant. And so what is the story behind it? Yeah, if we would like to get some informations, rough predictions or estimates of the forces which are acting in all the joints of our body while we are performing some movements, we have to know or have an assumption how much force each of the muscles in our body are generating during the motion. Because of the lower lever arms, it's the contribution of the joint torques based on the muscles are roughly 4 to 5 times higher than the contribution of the external forces. This is the first story. The nice thing is that our computer models that we have at the moment are able to do these kind of calculations. Yeah, when I say this, I would like to give a very short overview about the history of computational musculoskeletal modeling. So it started, let's say, 1970s, 1980s or so. There we got single joint muscles where between the two segments is one muscle placed, or maybe two muscles, and we can calculate what is the force that the muscle is generating during movement, and very simple muscles, simple simulations. I will show you later on one of them. Then later on, the models became more and more complex. So in the beginning, it was 2D models with up to 10 muscles. And from this, we got some rough insights about control strategies, very nice models from Amsterdam and from the US, and also some here in Germany. And but from this we got some information about muscle redundancies, and some studied also stability of movement, but it was still in 2D. And in the now in this century we have the computer power and also the methods that we are able to develop more complex models, three-dimensional models with a huge amount of muscles inside and optimization criterion, such that we can handle this in a reasonable timing. And there's very nice models, for example, OpenSim or anybody, as you heard just directly before me. And we have developed this computer model called Myonado, and I will introduce that model a little bit more in detail later. So this is my personal first steps in musculoskeletal modeling, which I did some years ago already, and I found this video, and I must say it was really funny. I made some simulations about self-stability, and this is a model based on one single knee extender muscle, and all the rest is just animation. So the red nose man is in this case stable, or in the other case the movement was unstable. And this will have been my first steps in computer modeling. And but now, as I said, the models become more and more complex and more human-like. So here we have now in the Myonado program, we do have 35 bones and 21 joints and nearly 700 muscles. Each muscle is described with force, length and force velocity. I will show you later on. We have a virtual reality technology, as you saw on the right-hand side, and we can animate the calculations, which is also very important to see what is happening in the body. We do that advanced inverse dynamics. So normal inverse dynamics is just stopping at the net torques in each joint, but then using the net torques, we have some optimization criterions to distribute this necessary net torque, as I showed you in this calculation at the beginning, between several muscles which are acting on that joint, because we have to do some estimations there at that point. Stop here. And we still are developing as everybody, I guess. And this is in a very close collaboration with the University of Münster, because I'm a professor there at the university, and this is really beneficial to have that ping pong between the company and the university life, and this is really very fruitful for us. So each segment in the model is described with a segment mass and the moments of inertia around the center of mass, and these parameters can be directly changed within an Excel sheet that we have developed. It's very easy to change that, or we can just scale it depending on body size and body mass, as you like. And you have for each of the joints is described with 1 to 3 rotational degrees of freedom, which can be defined individually. So we can open or close certain degrees of freedoms as you like. And we can drive these degrees of freedom by the measured kinematics. That would be the inverse dynamics way, or you can open the one or the other joint to be driven, to be moment driven. So you activate, for example, the muscles around the joint, and then you have a forward dynamics mode. And you combine both in a certain mixed dynamics idea. Yeah, and the joints are described with limitations and friction. I think this is what most of the models are doing. We have to deal with the external forces, as always. So if you do this, if you would like to get the information about the knee joint force, for example, also, then you need to know what external forces are acting on the body, and we can place where you like on the body and position, and you have, let's say, measured external forces, and then you can import this and drive, let's say, the arm, or include this information in the calculations. And we have the possibility to predict the ground traction force, but I will show you later on that one. Each muscle, 700 muscles nearly, I've said already, is described with these active and passive force length relationships, and it's close to what is measured and what is also used in the other computer models on the market. We have for each muscle the force-velocity relation, depending on a hip type force-velocity relation, as most of the models also have. And I think this is quite interesting. We have 3 different possibilities to optimize or to distribute the muscle activation or the muscle forces at the joint. So typically we have an overdetermined situation. That means that a degree of freedom of a joint, let's say extension and flexion, is driven by more than one muscle. So we have to ask how do we distribute now the forces which are necessary to drive that degrees of freedom between this overdetermined situation. And there we have included at the moment, we will extend that as well, minimization of muscle activation, minimization of muscle forces, or minimization of joint forces. And I think it's quite interesting. We have the possibility to merge between them, to say, okay, I would like to have 50% minimization of muscle force and 50% of joint force, for example. And this can be changed as you like. Okay, so if we have that model now, and if we have the data from the ComputerMyoGraphy study with the prosthesis, now it's a possibility to check how good are the prediction of the calculated joint forces compared to the measured ones. And this is really nice to have this data. And as you can see here, this is data for squatting on the left-hand side and walking on the right-hand side. The black line and the shaded gray area represents the mean and the standard deviation over the 6 subjects, patients with the prosthesis. And the superior force, this is the lower trace here, means this is the force which is directed into the tibia. And here in the first row, you will see, you're seeing the medial lateral and the anterior posterior forces in that tibia joint. And again here, black is measured data and dotted measured, and red is the prediction from our Myonado program. And you can see that we are really close by. We are quite happy about that. Very good agreement. If we increase the co-activation of the muscles, which would be possible, easily possibly, then we would be directly on the black line more or less. But we don't want to make a fitting or something. We just wanted to see how good is the prediction already based on the optimization criteria we have used. To check the optimization criteria, we have done this strange figure here. I would like to explain it a bit more in detail, checking the timing. Okay, it's fine. So you can see here the root mean square error between the predicted and the measured forces. Yeah, and the upper row is the squatting movement, and the second one is the walking situation, and we have changed the parameter S. That means a 0 represents an optimization or minimization of muscle forces acting at the knee joint. And parameter 1 means 100% minimization of the knee joint forces. And a parameter of 0.5 means 50% muscle force, 50% minimization of joint force. And as you can see, the minimum root mean square error is at a value of about, let's say, 0.8, 0.9. So it seems that the subjects here were using a motor control strategy on activation patterns for their muscles that are mostly trying to minimize the joint forces, which is quite reasonable if you have such a surgery. So this is therefore the simulation you saw in the slide before was done with a parameter of 0.9. Yeah. So as you can see, hopefully, I wanted to show that you can see that it is already possible to get a quite reasonable prediction of joint forces, including all the muscle forces acting at the joints during everyday movements, only based on the kinematics, and in this case with the external forces measured. But there are also other situations, not in the lab situation. For example, here in a sports hall, where we have measured with Xsens suit in our sports hall, and we have done our simulations with the Myonade, which you can see here on the left-hand side. But you can imagine that we don't have a complete set of ground traction force plates here in the sports hall. So it is necessary to get some estimates or predictions of the ground traction forces during these movements. And this is, as I would like to show you in the next few slides, this is also possible if you have or if you are using this kind of complex computer models. So what is the basic idea behind it? There are some approaches using artificial intelligence and other optimization criteriums are also used. I want to show here an approach that we have introduced, not introduced, but we are using in our model. And this is based very simple on the Newton-Euler equation. F equals mass multiplied with acceleration. So if we have measured the acceleration of the center of mass based on the kinematics and our computer model, and if we know the body mass of the subject, then the mass of the acting at the center of mass, the force which is acting on the center of mass to drive the movement that we have measured can be directly calculated. And if the external and these forces which are driving the center of mass have to equal or have to be equal to the external forces on the body. And therefore, if we only interact with the ground, as in this situation, if only both foot are on the ground, we can say that the force calculated here, the center of mass force, must equal the ground direction force in general. It's the basic idea. The second one is, if we are standing on both feet on the ground, the force of the center of mass have to be distributed between both feet. So this is one challenge which have to be solved. And here there are also some different approaches. We have used an approach where we have distributed 18 contact points, which is very similar to the paper of Xsens et al. But the details are a bit different. I would like to show you. And you can see we have distributed these contact points below a foot. And for each of that contact points, we have calculated these transition functions, still close to what Xsens were doing. It's a normalized way to estimate the height of the contact point relative to the ground and the velocity relative to the ground. So this is velocity based and this is the set position. And so we get a contribution of each contact point. And we said that the center of pressure is more or less calculated by the position of a contact point multiplied of the relative contribution of this contact point. And if you sum that up, you will get the center of pressure. Let's say for the right foot, it's here, and for the left foot, the center of pressure is somewhere else on the foot. So 2 points below each foot. This is already first step to calculate the ground traction force. And the second one is, if you have now the vertical movement in the lunge, for example, here you can imagine that we can calculate the acceleration of the center of mass, and with the mass we can get the forces. But what about the horizontal forces? So if you have a purely vertical up and down movement, you will not get any horizontal acceleration in the measurement. So it must be that the horizontal forces are zero based on that idea. But it's not, because there are also some extra forces you can press to the right and the left, and if you sum them up, it is still zero. So there are horizontal forces, even though that the resulting force is zero in the horizontal direction. And so the question is, how can we estimate or predict these horizontal forces, even though that we have no acceleration in the horizontal direction? And here we have used a very nice paper or approach, which was published by Maus et al. And Lipfert and Mr. Andre Seifert. And it was published in Nature Communications in 2010. And they have introduced the idea of a so-called virtual pivot point, and I really like that idea. So what is the idea? So they found that if you plot the the measured ground traction forces relative to the center of mass position. So here, let's say this is the center of mass position, and you can measure the ground traction forces for both feet. And you can see here two steps, so left foot, right foot here in the left panel here. You can see this is the center of mass position. It's 0 by definition because it's relative to the center of mass position. And then you can see if you plot the ground traction forces, they are interacting, or there is a resulting point, a so-called virtual pivot point, where these ground traction forces are coming together. Excuse me for the wording. So this is the so-called virtual pivot point where these forces are acting at. And they found that for running, for example, you have a virtual pivot point which is above the center of mass. And if you look at the paper, you will see that it's different in different walking velocities, and they also showed that for animals it is the same idea. So, and we use now this, and you can see that if you use the virtual pivot point, you have also these horizontal components of the forces, and therefore we thought maybe it is possible to use that idea to predict also the horizontal forces based on the virtual pivot point. And this is what we have done in our model, and these are the results. So we have measured walking and lunge movements and some other movements as well with an Xsens suit, and we have measured the ground traction forces. Then we used the IMU-based kinematics and predicted based on this contact points idea, center of pressure idea, plus the virtual pivot point idea, and predicted then the ground traction forces. And this is the result. The black line is again the measured ground traction force, left foot, right foot, anterior posterior lateral force, and the ground traction force, vertical ground traction force. And as you can see, the predictions are really nicely following the measured values. And not also in walking, because this is the more easiest way for the predicting of the ground traction forces, because there you do have these horizontal accelerations already, but also in the lunge movements where you don't have them. And even though we have a quite nice prediction, there are some differences, but only in a very small area. So the values are not so high. We have changed to analyze that the virtual pivot point position. So 1 means it is the virtual pivot point is at body height. 0.5 means nearly the center of mass position. It's 0.5 of the body height, and 2 means the virtual pivot point is double as high as the body height. And we changed that for the walking and lunge movements. And you can see for low virtual pivot point positions from 0.2 to 0.6, let's say, it's still a decrease in the root mean square error between the prediction and the measured values. So we assume that maybe a visual pivot point position of 0.9 or 1, 0.9 would be the position of the ear, more or less. And this could be a good assumption to use as a standard for the prediction of ground traction forces. But you can change that. I guess I will do some studies in this direction to see how different movements may result in different virtual pivot point positions depending on the stability, for example, which is necessary to perform that movement. Yeah. Thank you very much for attending this talk and giving me the possibility to present our work here. And I hope that it was maybe inspiring, and maybe hopefully you will have some questions after that. Thank you very much.
The first question from Surush, he is saying, based on the IMU kinematics, just foot orientation can be measured the center of pressure. Based on the IMU kinematics, just the foot orientation can be measured, or the foot center of pressure. So basically, do you guys measure the foot orientation, or can you also measure the foot center of pressure with the kinematic system?
Yeah. So yeah, thanks for the question. You are right that we can get the information of the foot orientation relative to the ground. And if, for example, the foot is touching or is in this position, then the center, the contact points which are distributed below the foot, you can see that the contact points at the tip of the foot are already close to the ground, and the heel center contact points are not. And therefore, based on the on this algorithm that I showed you, you can directly calculate, or you will get the information that the center of pressure below the foot is in the front of the foot. Yeah, and this is what we then use for the calculation of the ground traction force. I hope that this is more or less the answer that to your question. So we cannot directly measure the center of pressure from the kinematic system. This is not possible, but with that algorithm, we can have an estimate where the center of pressure will be.
Thank you very much, Heiko, for the nice explanation. I hope that this is the answer Sarush was looking for. Otherwise, feel free to pose another question in the chat. I also have a question from Cherry Gozai. He says, why don't you use the body model to compute ground reaction forces under each foot? Can you give an example of a successful application?
I don't know whether I understand the question the right way. So we are using the body model to calculate the ground traction forces. But if you have the body model, if you mean with the body model, for example, the segments and joints, so the mass distribution and the local accelerations of the segments, and from that we get the center of mass acceleration, and from that then we get the ground traction force. But the ground traction force, if for example, in vertical direction, it is quite easy to get that value, but in the horizontal direction, as I said, there could be an acceleration of 0, but even though you will measure horizontal forces, and this is why we introduced the virtual pivot point idea. And the second problem is that you get one value for the center of mass forces, but you have two places on the ground. If you have both feet on the ground, then you have to distribute the force of the center of mass between the 2 feet, and therefore also you need this algorithm. So it is not a straightforward way to get the forces below each foot differently, only based on the kinematics, and the algorithm should give a solution for that problem, or challenge, that I should say.
Okay, Heiko, thank you very much for the explanation. I think it was a good answer to the question. There's another question from Anand Bhushan. He's basically asking, can you use data to predict possible injuries or economic risk? Can you maybe elaborate a little bit on that?
So I guess, so we can, I would like to answer that in a certain way. So we cannot say a force equals an injury. This is completely strange, the idea. But what we can say is, if we cannot say that a certain joint angle will result in an injury. But I think from joint angle to injury, I think it's closer if you have the joint forces in the joint. So if you know maybe for certain movements which real joint forces acting or muscle forces are acting in the joint, then we are very close to the cause of a possible injury. I cannot say that the force in the joint are the reason, maybe, or as a direct one-to-one prediction of injuries or so. This is not true, but I think if we can do it in a different way. If somebody do have an injury, or maybe a chronic injury, and you have we make such an analysis and see that there is quite high joint forces in the movement, then it could be advantage maybe to trying to reduce these joint forces in order maybe to prevent further injuries. This could be possible. Yeah, this is why I think this kind of measuring or calculating joint forces is really advantageous for this medical or preventive area in sports, for example, as well.
Okay, thank you very much, Heiko. There's another question from Soran, and he is asking whether the VPP, vertical distance from the center of mass during running, would be the same as walking.
No, it's not. So this is what is, I think that the VPP position, the vertical position of the virtual pivot point, I think this is what the question is about. In the paper of Mouse, they show that this VPP position is slightly changing depending on the running velocity, for example. And you see also some individual changes. So, but as a standard, 0.9 seems to be for our situation a good one, and there must be some more for specific questions and specific movements and maybe specific persons with injuries, for example, or elderly people, or whatever you think about. It is would be quite interesting to do these VPP measurements and to see which kind of VPP values are here should be used for this population, for example. I think it's a really interesting future area to make some studies about that. I will do it. I can promise.
Okay, very good. Thank you, Heiko.